Okay, can you hear me, folks? Yeah, excellent. So the first thing to say is that this is, we should probably have that up there. Yeah, excellent, thank you very much. So the first thing to say is that this is a beta version of this talk, so if it stops in the middle or you have to hit Command or for me, this is all operating according to expectations, feedback, etc., gratefully received. Okay, where is my thingammy? Okay, so why am I here? Why would you care? Your plane's only a couple hours away. So leaving aside CV, blah, 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 reasons, the reason I'm here is basically because of this thing, of which I was the instigator inside Google. Obviously, SRE at Google thinks a lot about operability, and we care a very large amount about related issues. This talk is essentially taken from the chapter of the book about automation, and I attempt to relate automation and operability in this talk. Actually, I guess, as a function of that, could I ask folks to put their hands up if they've read this book? Excellent, my talk is still valid for 86% of you. Okay. So for those of you for whom it's not relevant, please feel free to continue to browse the web as you were previously. The talk does construct things in a slightly different way, but okay. Actually this window is not behaving as if it should be. Hence beta. Sorry, 1 second. I have to just close my speaker notes and move them back. Excellent. Okay, so firstly, stating my assumptions. So here I have a diagram showing highly approximately how SRE and product-focused development engineering have particular areas of concern within Google. So I've heard this phrase full stack. So to me, full stack is hardware to user-facing JavaScript. Above user-facing JavaScript, we have sublimed to pure energy, and so it's outside of the domain of concern. So you will see at a glance from the diagram that, again, within the Google context, the difference is that the spread of expertise, if you like, or the domains of concern are approximately equal in size, but product development tends to be shifted up the stack a bit, and SRE tends to be shifted down, as perhaps befits our concerns about reliability. You never really-ish find SRE writing user-facing JavaScript. You almost never find a classical web services product suite writing a disk driver. Okay, it doesn't really happen. It's more complicated than that, but you get the basic idea. So, hello. Oh, excellent. Okay. Next. Cool. So, a minor modification to that diagram is if you look at the normal distributions, or well, Gaussian-ish anyway, that picture is an attempt to represent where we spend our time as opposed to what our overall domains of concern or expertise are. Increasingly inaccurate as this analogy is, what it does show is that we spend most of our time at the layers kind of above POSIX, but nonetheless infrastructure. Or below UI and business logic, although we do business logic from time to time. And as service owners, again, in the Google context, SRE owns the product in production. We work a lot on automation. We want to make our jobs go away. Historically, we've not been very successful at that, but okay. So, that guy on the right is Federico. Why do you think he said, well, we've got black art and we've got automation, like they're pretty similar, right? We have this deep ambiguity about automation in the industry, I think. Maybe we're even pretty uneasy about it as a species. never mind a job role, as reflected by the comment that anything that's done automatically for you can be automatically done to you as well. I hope to illustrate with this talk that, in fact, some, if not all or most of this unease is misplaced. So, anyone know who that guy on the right is? Philosopher? Plato. Yeah, very good. On average, all philosophers are Plato, right? So, coming back to the theme of the conference and attempting to relate automation with operability, we care because these are related quite closely. Yeah. So let's think about the platonically optimal piece of software, okay? Does it have great operability or does it have poor operability? It's got great operability, absolutely right. We don't want something that's just failing all over the place that we can't actually operate. So it definitely doesn't need poor operability. So how do we define poor operability? I mean, I know a lot of us would have a fairly intuitive conception of what that might mean from our jobs, if nothing else. So one important thing that folks often discover is they need to do a thing with a piece of software, and it doesn't actually have the knob to allow you to do that. Oh, geez, I really need to throttle the incoming RPCs to this piece of software, but it doesn't actually have the configuration or the flag or whatever to allow me to do that. So that's an important limitation. Not having good inspection or inspectability. So poor logging, I guess a tool that emits okay when everything is fine and emits nothing when everything is broken is not the platonically operable piece of software. And dashboards and so on and so forth. Introspection. Another place where we might vary from great operability is if the behavior of the software is different to what we would expect. Perhaps the documentation says it will launch in this way and it launches in this other way. Or it behaves non-deterministically. I know that despite computer science theory, we have all dealt with pieces of software that behave non-deterministically, and that's not great. And another very important one, which is software that's kind of fiddly or extremely sensitive to maybe minor variations of libraries provided or the running environment, or even data-dependent software or some characteristic of its running that depends on the incoming data and so on. So all of those are pretty poor, okay? So great operability. What's great operability? It's not the opposite of those, though. Not necessarily, right? The platonic piece of software I claim, for the purpose of this talk, is not that it's perfectly automated or has the logical inverse of all of those properties there, but that it's autonomous, that it runs itself, that we don't need to improve the affordances to the operator necessarily, because it doesn't need that. Okay? So, coming back to that again, if we had a place in the code, or writing a server or some tool or something, doesn't really matter, and we had an opportunity in that code to provide a well-behaved interface to the operator or some fluid, well-put-together piece of engineering, and we didn't do that, we also missed an opportunity to provide an automatable interface or some kind of affordance that we could use to control the software later. Or we missed the opportunity not to provide an interface because we don't need to provide an interface because the software itself will take care of the conditions for which that would have been necessary. So obviously this doesn't apply to everything. We'll talk about some of those exceptions shortly. But I would encourage you to think about inverting the problem and think about this statement and what it might mean for the software you design and write yourselves. So if we happen to believe in this paradigm, note that paradigms are things that you believe, not things like gravity. You can't test them. Paradigms are a little more like pure energy than that. But the paradoxical conclusion under this paradigm is that better operability is served by not necessarily facilitating manual operation or error recovery, but by making the software autonomous so that you don't have to do that in the first place. So, better environmental reactions on the behalf of the software, fewer dependencies, fewer fiddly dependencies, no data-dependent behavior, sane error recovery, and inspectability, maybe for the machine as much as the operators. And all of these would be good in the context of understanding how to write autonomous software. So in the chapter, we spend quite a bit of time talking about what the value of automation is. Again, coming back to our conflict in the industry about the value of automation, we fear, I feel, as an industry, that if we do actually take the effort to go and automate something, that we will then have the additional burden of maintaining that software, as well as doing the stuff that we thought the automation would fix, but in fact doesn't, or maybe partially fixes, etc. As illustrated by XKCD. There's another wonderful cartoon in this context, which is the precise diagram of how much time you should put in to writing a piece of software and figuring out how much time that's going to save you on an ongoing basis. In fact, as the chapter suggests, the benefit of automation is not necessarily in time savings. So this diagram, while being mathematically useful, is in fact not the whole picture. So, talking about the value of automation for Google SRE, when we automate something, and again, for the purposes of this conversation, I'll be platonic about it, or I'll be philosophical about it. We're going to assume we do this perfectly or somewhere close to perfectly, just to talk about the gross differences. So consistency, if something is automated well, what that brings to the execution of that automation, what you get out when you do it. So obviously any action performed by a human hundreds of times, maybe with manual steps in a row, is not going to be performed the same way every time, or at least the discipline required to do that is fairly extreme. We wouldn't necessarily expect it for any reasonably sized endeavor. So that lack of consistency leads to mistakes, oversights, issues with data, failures, blah, 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 and reliability problems, of course. So the value of consistency is in many ways the primary value of automation from the viewpoint of SRE. So faster repairs is an interesting one. Considering the case of automation that's somehow fixing things or cleaning up stuff. Automation that's fixing problems, which is very common in the SRE case, if the automation runs successfully enough and regularly enough, what happens is that across some domain of production which has some things wrong, every time you run the automation, you groom out a certain number of problems. And it turns out that this reduces MTTR for other things that you're doing, because the statistical chances of encountering something in the course of resolving the problem are less, because your automation has groomed away the minor, or even medium to major things, depending on how advanced the automation is. Additionally, I think it's well understood in the industry that the later you are in the product cycle, the more expensive the problem is to repair, with the most expense being encountered, of course, when that problem is in production already. Generally, in terms of times and money, an automated system looking for things very regularly as soon as they're encountered, bringing that time to repair down is good. Now, faster action is, of course, fairly intuitive. Humans don't usually react, in certain cases, as fast as machines. In very common cases, certainly within Google, where we have some kind of failover situation, either data-related or QPS for load balancers or whatever, that can be well enough defined for a particular application that we can have the automation react much, much faster than any human could possibly do anything, really. In the limit, of course, this represents a statement that it's useless to have a human around continually pressing a button which is labeled allow system to continue to run. Press, 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 press. So if that's how we're going to set stuff up, like maybe we could improve that. And also, again, specifically in the Google context, Google has a very large amount of automation. In fact, some of the systems many years ago crossed the threshold where they were manageable manually, and we ain't going back. Like there's no way to go back from that situation where you need the automation to continue to run. Time savings, as discussed. One interesting subtlety, I think, that's not often discussed is that the benefit of the time savings is often not as immediately calculable as that diagram would have led you to believe. For example, it's easy to overlook the fact that once you've encapsulated some task in automation, you've saved that time not just for the person who wrote it, but for all of the future people who might run that automation, or all of the organization that might benefit from it. So that diagram being from the point of view essentially of one person, if you divide the total number of beneficiaries, or if you divide the time by the total number of beneficiaries, you can often end up with that equation looking considerably different. And very importantly, if we have, again, the platonically perfect written piece of software, which does not exist. When you have the automation finished, you have a platform. You have something that can be extended, something that can be applied to more systems, something which is maybe well-defined on inputs and outputs, which implies that it could possibly even be spun out for profit, or otherwise manipulated as a piece of software is today, rather than understood as an aid to manual operation. A platform also centralizes mistakes. Hooray, I like my mistakes to be centralized. Do I? Well, the best thing about centralizing mistakes is that if you have a bug in one place, you can fix it in one place, whereas if we all have forked copies of the shell script to copy the stuff around in different home directories, that bug can lurk in many places and can be quite problematic to remove. Also, depending on the particular situation, the automation can run continuously, or certainly run more frequently than humans would wish to execute it, or at times that are inconvenient for humans otherwise. And a platform can export metrics about its performance, so you can figure out what it's doing more easily and improve the areas which are falling short. So, do the automation maybe not necessarily for the people, although it's useful for time saving, but also for the platform. And the platform pushes you towards which in my view is incredibly valuable, pushes you towards thinking of things as autonomous systems. So in that context, our experience with automation in Google SRE has been, in many cases, the same as essentially everybody else's. We start off with no automation. So, for example, the database master. A database master failover has a load of people clustered around big monitors and people shouting commands at them and so on and so forth. And now we move over to some kind of externally maintained, i.e. not necessarily first-party maintained, specific automation. So we've some kind of failover script somewhere. Oh yeah, Jennifer has that in her tilde bin. Let's use that. Or we can have more powerful, or at least more generic automation. There's a generic failover script that everybody uses, and we add database support to it. Or we can have internally maintained, but somehow system specific. Maybe the database ships with its own failover script, with the idea being that the people charged with the development of the database and its correct operation are also charged with updating that software when they change something on their side. And organizationally speaking, as we'll see later, when you separate out responsibility for automation maintenance versus the underlying systems and how they behave, that's often an anti-pattern, often results in bad things. And then systems don't need any automation. The database notices problems itself and automatically fails over without human intervention. Okay. So, a couple of examples here. Again, these are basically from the article, or from the chapter, I should say. So, way back when, years and years, Google had a database, it turns out. Turns out we also, we put ad stuff in that database because we thought maybe it would be good to keep data on ads. And we also put an SRE team in charge, perhaps unsurprisingly, because we wanted that database to have somebody to look after it and keep it up and so on and so forth. So after a while, we got to a bit of a local maxima, actually. We got to a kind of a plateau in the life cycle of that team and their relationship with the software they were looking after. We had failover scripts in what I'm going to say were not tilde/bin directories for the purposes of this talk. And we had most of the routine work automated away, so replica cleanup or failover, stuff like that. We thought we got to a fairly good state. But what happened over time was that the continued growth of the ads business and also the development of a system we called, in a staggering lack of awareness about how this would be perceived by PR, Borg, cluster scheduling system, pushed us to rethink how we actually did this. Borg did a number of things, and we'll actually go into this in a little bit more detail later. Borg allowed us to think of eliminating entirely the machine level or replica level maintenance problem, setup and restart of a container, Borg's a containerized system, to run MySQL instances would be taken care of completely automatically. And it would also, which was a concern given the growth levels we were experiencing, it would also allow us to make much more efficient bin packing decisions, as containerized systems generally allow you to do. It wasn't easy. In fact, it was hard. So it turned out that we had architected our system, and by which I mean the entire set of human procedures and software and so on. We could architected our system around the fact that because failovers were expensive, master failovers, I mean, in this particular case, because failovers were expensive, we wouldn't do them very often. And so the fact that Borg, as it was deployed at that time, would not provide you any guarantees about how long your job would run in the same container. In fact, not that it would provide the converse of that, but statistically speaking, you could depend on your task being restarted a small integer n number of times a week. Was a challenge for us. It was kind of okay for replicas, but it was certainly a lot more difficult for master failovers. And master failovers in those days were extremely problematic events. Well, no data loss occurred, but they were difficult events with lots of people clustered around monitors and shouting things. They typically took between 30 and 90 minutes, were very human labor intensive, and gave us, in general, a best case availability which did not meet the business goals, which you'd think would be kind of bad. And you'd be right. So, in fact, when we ran the numbers, the error budget that the business decided on required a master failover time of 30 seconds or less. So immediately that told us that we cannot optimize a human-driven procedure to meet this target. That's gone now. Can't do that anymore. We have to automate. So, and can't just automate some things, have to automate more or less the full life cycle of the system operation. So we wrote a program called Decider. I'm the decider, sorry. We were successful enough in writing this piece of software that it turned out we could meet the 30-second target about 95% of the time, which was within business goals. And we moved from, as I was saying, having structured the existence of the team kind of around the fact that failovers were expensive. We just accepted that as, previously, we just accepted that as a fact of life. Oh, can't change that. Or perhaps more accurately, it would be too expensive to change that given the benefit that we could get. But in fact, the benefits that we could get turned out to be more than we initially assumed. And certainly the meeting the business goals for the availability of the service would have been a big one. So, as I say, we moved from attempting to avoid failure to embracing the beautiful inevitability of failure, but not without cost. So, as well as writing special software to support the notion of master and replica failovers, and figuring out how to do correct instance setup for Borg containers, and a whole bunch of other stuff I won't bother you with. We also had to change a lot of the client-side logic, because many of those clients would have assumed fairly implicitly that if they got a database handle at the start of the execution, that database handle would remain valid for the length of the computation, or at least the length of the lifetime of the process, which turns out it's not true, okay? But we got a lot of great benefits. So of course we made the SLO. But also, the time we spent on what I'll call mundane operational tasks, kind of replica cleanup and, hey, where are the logs for X, and B, what do we have to do about the caches on this thing over here? That kind of time, the time we spent on that dropped 95%. So we just could entirely ignore that class of problem, which was amazing. In fact, and here's where we come into the virtuous circle piece of the argument. The free time that we saved from automating away those tasks went into improving the other things, which improved our free time, which went into automating the things, which improved our free time, which went to, and so on and so forth. So, as well as all of that, with the attendant bin packing changes and efficiency gains that we made from related activities, we freed up about 60% of our hardware resources. Not bad. So, a quick digression on failure. My career has been filled with failure. My job is very literally filled with failure. When people ask me what my job is, I say I'm a professional pessimist. I'm a natural pessimist as well, but that means I get an advantage when I'm a professional pessimist. So talking about client-side logic and the assumptions that are made that a database handle remains valid for the lifetime of your process and so on. In fact, if you consider a simple HTTP transaction, well, the client computer can obviously fail before the socket's opened, right? You could run out of memory to construct the socket. The process could or something like that while after it's made the socket, but before we were actually delivering packets. The network card could fail. The various things in the network between source and destination could fail. The receiving process could fail. It's just failure all the way down. It requires a particularly destructive intelligence to think of all of those things that could go wrong, by the way, which hopefully all of you possess. Anyway, I guess the meta point I'm making here is that, as I understand it, this point having been made in the conference multiple times already, that for something sufficiently large, there's failure, ephemeral failure at some point in a sufficiently large system somewhere. And the way to react to this, scalably anyway, is not to say, okay, we'll husband our resources carefully so we don't experience failure that much. It's more about writing automation so that the system can be operable as this happens, because it will happen and does happen. I guess this kind of thinking isn't typically taught in undergrad degrees or anything like that, or where they tend to focus on the single machine case. Okay. Anyway. So, example 2, having finished MySQL, cluster turnups. So, way back when, and also today, but definitely way back when, cluster turnup was a material cost, material effort. Like, it actually made a significant difference, still does, and extremely complicated, still is. So, of course, we gave it to newbies. We gave it to newbies because we said, this will be a good exercise for people to go through in order to learn how the systems work. And as they encounter the problems, because they're fresh and new and innocent, they'll be highly motivated to fix them, so that's going to work out. So it turns out that that didn't necessarily work out, or at least that there were some benefits as I've outlined, but the costs were also significant. And even though some of the nooglers, as we call them, I'm very sorry, some of the nooglers would definitely have been motivated enough to fix things. They didn't necessarily have the persistence or the schedule to actually fix some of them in the limit. And anyway, it's a hard problem, okay? So there's lots of dependencies to a cluster turnup. Not only are the standard set of infrastructure services that you're all familiar with, DNS, DHCP, blah, blah, blah. I guess I can say that. There's also fast-moving, more proprietary services. Google actually looks like a lot more like an enterprise software business that happens to specialize in data center infrastructure than an advertising company, if you look at it the funny way. Anyway, so there's on the order of hundreds of kind of underlying subsidiary dependencies, et cetera, in order to get a cluster in operation. And it was generally error-prone, leaving aside the fact that we initially tended to give it to Nooglers. It was also, in such a fast-moving environment, very easy for example, one system to make an assumption that if you happen to not have a 0th disk, which you are using for logging, that the system is therefore, its disk is gone and it should be put into repairs, which led to a multi-petabyte big table data loss, which we had a live copy of, so that's okay. And the automation, the automation at that stage was SSH-heavy, kind of free-form shell scripts, essentially. And making that step from manual operations and like copied and pasted commands and stuff like that to free-form scripts SSHing around was actually a useful improvement. So that initially brought us wins in dropping the time to service of a cluster. Those scripts were kind of cholesterol, right? They taste good when you're doing them. Sugary shell scripts. And then you have 1,000 of them, and you're, that doesn't feel so good. So we decided to take a slightly different approach. And we came up with a framework which used the basic idea of Python unit tests. Okay, so this would test the state of a cluster, called prod test, and run on a cluster. It spits out the list of differences from the expected configuration of the cluster, which in a very quickly moving environment with lots of infrastructure changing is very useful. So here's an example of the kind of thing that prod test did. So there's a list of tests there. You can see cluster exists in machine database. Well, the cluster has to exist in the machine database, otherwise we can't do anything else. So that's one test, and so on and so forth. You can follow the logic there. In this particular case, the failing test in red is to do with whether or not we have a monitoring config for the core DNS. The major benefit of this, and obviously the tests, depending on that, are also going to be failing tests. The major benefit of this was that it's centralized and also externalized from the teams the definitive list of setup steps required for a cluster. That list is sufficiently long. Coming up with a definitive list of it, definitive iteration, is actually quite hard. Another major benefit of it is that it brought predictability to the process. We could definitely say, we would just run the script and it would spit out the 6 things that were wrong or the 600 things that were wrong. And we didn't have to go and ask a bunch of different people what was happening. So that was fine. The next mission was, of course, to turn up 5 clusters in 1 week. So that was absolutely terrifying. So we had tens of thousands of free-form shell scripts all over the place, owned by dozens of teams. Okay, basic idea, we will pair the fixes with the tests. So we'll run the test, and we'll encode logic which will fix the problem and then run the test again. So here's a diagram of what that looked like. So in this particular case, test DNS monitoring config exists as failed. We punt to the fix code, and then it worked. Fine. It had important limitations around the idempotency of the fix, which turned out to be rather more important than we thought, but it did work. It did work, and it was fatally flawed. And it was fatally flawed because the tests became flaky because the latency between the fix and the test and the rerun was such that you could have things failing and succeeding if you ran them after each other. So we moved everything to a centralized team. One team to look after this. Framework is complicated, difficult for other people to master. And it's kind of handier to have a single team to kind of, as your leverage point. But this changed the organizational incentives. So the DNS team now no longer had a great incentive to keep their automation up to date because somebody else owned it. And we ended up not being able to change our scripts as fast. So we moved from a situation where our tests were accurate, or our automation was accurate, and was slow, but it did a lot of what we needed to do, to a place where the automation drifted from what needed to be done, where it was slow, and where it didn't get everything done that we needed to get done. So not actually a win as such. And incentives matter, as any economist will tell you. All of the teams partaking need to have the incentives to do the right thing. So we needed to change, particularly as a result of the China incident, and we moved to a service-oriented architecture approach, where the lifecycle responsibility for a service was pushed to the service team. And so the DNS systems, the config for the DNS systems ended up being pushed back to the DNS team and running through admin servers to which permissions could be delegated. And we ended up going through the same automation hierarchy as before. And finally, I know I'm over time, our cluster started like everyone else's, a bunch of machines named after Star Wars planets, and racked kind of heterogeneously and so on, stuck together with hope and shell scripts. And then we had Python, so we automated some of that, which allowed us to move one level up and manage the machine lifecycle, particularly with the machine database that we ended up building later on. But at the end of the day, that system was too intensely tied to the specific existence of physical machines, and services were tied to those physical machines in turn. So we had a high proportion of essentially mandatory operational work to manage that. And so our reaction was to move to cluster management as an API, as a service. We would have an API for creating jobs and downing jobs and changing them in some way, which decoupled scheduling as such from physical reification. In other words, you didn't say, I want my machine, or I want my service X to run on machine Y1. You'd say, I wish service X to exist. And sending that RPC to the correct machine would instantiate this, which meant that we got to a very organic state where we could change one bit, like our skin molecules are supposed to cycle every 6 months or something like that. We could change a bit of the system at a time for kernel updates, etc., and continue just fine. So thousands of machines today come into service, have some problem, die, and are reborn without any SRE having to do anything at all, which is autonomous and not automated. And I'm done. Thank you very much.